When you perform a maximum likelihood estimate for the normal or Gaussian, you usually see something of this format. I claim that this can be rearranged into something where the mu is outside of the summation. Something similar holds true in the multivariate case with the precision matrix lambda. In this video, we will derive both of the cases of something that's called the sum of squared differences from the mean. Hi, welcome to this new video. Let us start with the univariate case. And for the univariate case, or scalar case, we have to show that the left-hand side is equal to the right-hand side. So we have to show that the summation from I0 to capital N-1 over the observations minus the mu in brackets squared, so the squared distances from the mean, is equal to the summation from I0 to capital N-1 over the squared differences from something that I will also call the mean, I will introduce shortly, squared, plus n times, where the n is the number of samples, times the x bar, that we also have here, minus the mu. And the x bar is 1 over n times the summation from I0 to capital N-1 over xi. And if you watch the video on the maximum likelihood estimate for the normal or Gaussian distribution, this is nothing else than the MLE estimate for the mu. Okay, let us start with this equation, and first let us expand the square of the bracket. So we get the summation from I0 to capital N-1 over the xi minus the mu in brackets squared is the summation from I0 to capital N-1 over first xi squared minus 2 xi mu plus mu squared. And then let's apply the sum to each of the components individually. So we get the summation from I0 to capital N-1 over xi squared minus 2 mu times the summation from I0 to capital N-1 over xi plus n times mu squared, because there is no I inside of mu squared, and for this we can just add it up n times, which will be n times mu squared. Let us look back at the definition of the x bar, which was the maximum likelihood estimate for the mu or for the mean. We can rearrange this here in order to get that the summation from I0 to capital N-1 over xi is n times x bar. And then we can replace this here with n times x bar. When we do this, then we can factor out an n from the last two terms, and we have the summation from I0 to capital N-1 over the xi squared plus an n times a mu squared minus 2 mu x bar, closing brackets. Then we see that this looks really similar to a quadratic form. So if we would have a mu minus an x bar in brackets squared, it's just missing the x squared component. So let us add an artificial x squared or x bar squared minus an x bar squared so that we can complete the square. If this is a little strange to you, then you can also just use the classical strategy for completing the square. Let me note this down so we will complete the square. Let's do this and then plug it in. So we have the summation from I0 to capital N-1 over the xi squared plus an n times mu squared minus 2 mu x bar plus x bar squared minus x bar squared. We see that this will then be a mu minus an x bar in brackets squared, right? You can check this by multiplying it out. And we are left with minus an n times x bar squared. So we have the summation from I0 to capital N-1 over the xi squared. And here we then have plus n times mu minus x bar in brackets squared minus an n times x bar squared, which is already getting close to where we want to be, because recall, we wanted to show that it is of this form. So we have to move the rest into this expression, which will be a little tricky. And for this, let us add, again, an artificial zero, which will be plus n times x bar squared minus n times x bar squared, because this minus this will still be a zero. And then we get the summation from I0 to capital N-1 over xi squared, so our observations squared in essence. Then let's simplify this. We will have minus 2 n x bar squared, right? Because here and here. And then plus n x bar squared plus n times in brackets mu minus x bar squared. And we know that x bar squared is nothing else than x bar times x bar, and n times x bar is the summation from I0 to capital N minus 1 over the xi. I hope this makes sense because that is what we derived earlier here. N times x bar is the summation. And here we see we have n times x bar squared, and this is the same as if we would add up x bar squared n times. So this is the summation from I0 to capital N minus 1 over x bar squared. Hope to see this. Like if we would add this up n times, then we would get n times x bar squared. If we put this in, then we have the summation from I0 to capital N minus 1 over the xi squared minus 2x bar times the summation from I0 to capital N minus 1 over xi plus the summation from I0 to capital N minus 1 over x bar squared, and then of course the term that we already found, which was n times mu minus x bar in brackets squared. And if we look at this is the same as we did here, where we broke out the summation to each of the components individually, so we can join it back together. Then we have the summation from I0 to capital N minus 1 over the xi squared minus 2x bar xi plus an x bar squared, and then closing brackets for the summation. And here we have n times mu minus x bar in brackets squared. And then we see this is nothing else than another quadratic equation, which we can bring into standard form. We don't even have to complete the square, we already see it, that this is the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared plus an n times mu minus x bar in brackets squared. And that is what we had to show. Just a quick note why this is useful. This is useful because then the mu is no longer in the summation. So just to answer the question why mu is no longer in summation, and that can be extremely helpful for further derivations for certain Bayesian analyses. With the univariate case in mind, let us now continue to the multivariate case. The multivariate case was given as the summation from I0 to capital N minus 1 over the difference in the ith observation. Recall this is a vector minus a mu vector transpose times the precision matrix lambda, which is just to note this down, this is nothing else than the covariance matrix inverse, times xi, again, the ith vector observation minus the mu vector, and then closing brackets for the summation. And our task is to show that this is equal to the summation from I0 to capital N minus 1 over the xi vector observation minus the x vector bar transpose times the lambda of the xi minus the x bar plus n times x bar minus mu vector transpose and then the lambda and then the x bar minus mu. And you see this is just the multivariate generalization of a quadratic form. And you see one major difference in the formula that we derived before. We didn't have any information on the variance. This is because usually in the Gaussian, the variance is also in the exponent, but it's just a scalar value, so we can just commute it around in the multiplication. But here it is an essential component in the quadratic form, so we have to also keep it during our derivation. But it does not greatly affect the outcome of this derivation. So let's start again with this form and multiply it out. So I will write it down once again. We have the summation from I2 capital N minus 1 over the xi observation minus the mu vector transpose times the lambda matrix and then the xi vector minus the mu vector. And then let's factor it out, and we have the summation from I0 to capital N minus 1 over first xi transpose lambda xi, which is this times this times this. And then we have the mixed term, which is minus 2 mu transpose lambda matrix xi observation. And then the second quadratic term, which is mu transpose lambda mu. Let's break out the summation into its corresponding pieces. We get the summation from I0 to capital N minus 1 over the first term, which was xi transpose lambda xi minus 2 mu transpose lambda times the summation from I0 to capital N minus 1 over the xi vector observations. That looks a little strange, but if you add up vectors of the same length, then you get another vector. So this is like somehow legit. So we still multiply our lambda matrix with another vector. And then here we don't have any I anymore, so we have an N of a mu transpose lambda mu. Let's go back up and also introduce the definition of the x bar, similar to what we did in the univariate case. And we have that x bar vector here is 1 over n times the summation from I0 to capital N minus 1 over the xi vectors. And then we can also rearrange this and get that the summation from I0 to capital N minus 1 over the xi observations is n times x bar. And of course, the x bar vector is our mu vector maximum likelihood estimate, as we've seen it in the derivation of the maximum likelihood estimate for the multivariate normal. With this information, we can now find this again here in our equation as this expression. So the summation from I0 to capital N minus 1 over the xi vector will just be n times x bar vector. Then let's factor out the n, and we have the summation from I0 to capital N minus 1 over the xi vector transpose times the lambda matrix times xi, then plus n times, and first this quadratic term, which is mu transpose lambda mu, and then minus 2 mu transpose lambda x bar. Then closing brackets, and here let us add an artificial 0, which is given as an x vector bar transpose times the precision matrix lambda times an x vector bar minus the same thing again. And if we would plug this in, then we could complete the square for the first term, and we are left with n times this one. I hope this makes sense. It's similar to what we did also in the univariate case. So we have the summation from I0 to capital N minus 1 over xi transposed lambda xi, and then minus n times x bar transpose lambda x bar vector. And here we have plus n times, and now in brackets we have the quadratic form, which is x bar minus mu vector, then the lambda matrix of x bar minus mu vector. And then let's add another artificial 0 here, and this will be plus n x bar transpose lambda matrix x bar minus n times x bar vector transpose lambda x bar vector. We have 2 times this term and then 1 times this term. So let us write this down once. So we have the summation from I0 to capital N minus 1 over the xi transpose lambda matrix xi, and then minus 2 times n x transpose lambda matrix x bar plus n times x bar transpose lambda matrix x bar vector, and then of course the last term n times x bar minus mu vector, then the lambda matrix, and I forgot a transpose here, and also here we need a transpose. And then we can make the same argument as in the univariate case, that n times this one will be the summation from I0 to capital N minus 1 over the xi vector observations. Here we can say that n times this quadratic term is the same as the summation from I0 to capital N over this. So this will be the summation from I0 to capital N minus 1 over x bar vector transpose times the lambda matrix times x bar vector. And with this we can then factor out the summation and have one big term that we are taking the summation over, the summation from I0 to capital N minus 1 over, and then first this term, which is the xi observation times the lambda matrix times the xi minus 2 times, and it does not matter whether we put the xi after the lambda or in front of the lambda, and this is because the lambda is symmetric, and by this we can change the vector that is multiplied with it up front with the vector that is multiplied with it that is like behind the matrix symbol. In essence, this means we can have an xi transpose or xi vector transpose here and have a lambda matrix and then an x bar. And then we have the term which is quadratic in x bar, which is x bar transpose lambda matrix x bar vector. And then the term that was there quite early, which is n times x bar minus mu vector times the lambda matrix times x bar minus the mu vector. And here we are almost at the finish line. Now we can complete the square in this expression, and we are left with the summation from I0 to capital N minus 1 over the xi minus the x bar in brackets transpose multiplied with the lambda precision matrix of the xi vector minus the x bar vector, then closing brackets for the summation plus n times x bar minus mu vector times the lambda matrix, transpose of course, and then x bar minus mu vector. And with this, we are done with our derivation and have also shown that my claim holds in the multivariate case. Thanks for watching this video. If you enjoyed it, then I would really appreciate if you like the video and subscribe to the channel. There is more awesome content coming soon. Here you will now see similar videos, and I hope to see you next time.